Last time Mark did his chemistry of ironing thing.
I hate ironing.
Fair enough, I haven't ironed anything since like 2008. So what chemistry keeps my life working? Well, probably these things, which will be familiar to anyone with a small child running around. Nappies. This one here is reusable, which may sound a bit weird, but all nappies used to be reusable, and washing them used to be the norm until like the second half of the 20th century. And they're really good, actually. They're quite firm, so give good hip support for babies. They're easily put on and off for toilet training, and you can get them in much more fashionable designs. And they're becoming much more popular because of the high environmental impact of the disposable ones. We could definitely do an entire video on just that. And with enough reuse, these become significantly cheaper than the disposable ones over their lifetime. So why did these fall out of use to be replaced by these throwaway ones? Obviously, convenience is one thing. Bundling them up and throwing them away is very, very convenient, especially when things get messy. But it's also got a lot to do with the chemistry going on inside the disposable nappy. So let's do a couple of tests to see what these things actually do. First, let's pull this one apart, take the poppers out. Really the core, at least this particular model, is this insert here. So this is mostly cotton and cellulose, and let's put it down here. Right, so this weighs 55 grams. That's fairly heavy. Let's compare it to the disposable one for a moment. 30 grams. So this is actually certainly a lot lighter. So let's get some water and try this, shall we? And it's probably about 10 mil. You can see it soaking in here. Almost coming up to it being double. And it's still a bit wet. It's still quite soaked there. Let's 123. So a few times its weight, but it's not doing the best job here. It's holding onto it. It's not dripping, but it's not exactly leaving my fingers dry here. That's can mop up. So that's one of the things about these inserts and the disposable ones. They are just material that's holding on to water. So let's try what happens when we use the disposable. Let's try some water in this. Obviously, initially, it does splash in places because it is a hydrophobic polymer on top. But we know when you tell, it's actually leaving my fingers quite dry already. We're up to 50 odd grams. Let's give it another shot. This is really a little bit wet, but that's actually absorbing it quite nicely here. Let's keep going and see how far we can push this. And this is starting to bulk out. You can really feel the weight of this. 117. 150 grams. So we're now 2 or 3 times its original weight. And we can probably keep this going. It's just going in there. And what you can possibly see, if we look at it, it's really starting to expand a lot. So, firm jelly-like substance there now. And it's leaving my hand mostly dry. All of that water actually just hasn't seeped into the inner core yet. That's nearly 200 grams of water in there. I'm squeezing that quite firmly and it's not coming out. So we're up to several times its original weight in water. Let's keep going. Just let it sink in. No, it's okay. Now we're at the point where it might not be able to hold on to much more. Just about squeeze some out there. Yeah, so we started at 30 grams. We're now at 230, so that's 200 grams of water there. What's happening here is that the reusable nappy is mostly cotton, which is almost pure cellulose. That's absorbing maybe a few times its weight in water, but it's not holding on to it very well. The disposable, on the other hand, is taking on a lot more of its weight, and it's also holding on to it. There's some cellulose in there to support it, but there's also a super absorbent polymer embedded in it called sodium polyacrylate. Sodium polyacrylate is, like most polymers, a long chain of identical repeating groups, and each group in this polymer is a carboxylate group. That'll be familiar to people with a bit of organic chemistry under their belt, but for anyone who doesn't, it's pretty much the same group that makes organic molecules acidic. So things like acetic acid found in vinegar or citric acid in fruits, they have this group. The change here is that we've just replaced the hydrogen, which makes that group acidic, with sodium, which instead makes these groups carry a stronger electric charge. And it's that charge that attracts water really, really strongly through hydrogen bonding. It makes it hydrophilic or water-loving. So do check out Anna Maria's video on hydrophobes, which are the opposite and actually repel water very, very efficiently. But it's a bit more complicated than just these groups interacting with water. These groups aren't just holding on to one water molecule and that's it. A water molecule is only a fraction of the weight of this polymer unit, so if a polymer like this holds on to thousands of times its own weight, each carboxylate group isn't responsible for holding on to the equivalent of just one or even tens of water molecules, but hundreds of them. This is where we need to zoom out just a little bit. These polymer molecules are huge, maybe thousands, sometimes even tens of thousands or hundreds of thousands of units long, and that gives the polymer a complicated structure. The long chains wind around each other, they also cross-link together, creating kind of a porous pocket-like structure when we zoom out and look at it. The polymers are held tightly by these cross-links, which stops them simply dissolving in water, but they're held loosely enough to expand. After it's absorbed the water, we class it as a hydrogel, and it's this really squishy, gelatinous substance when you feel it. So let's try cutting into it. See what's in here. There it is. You can actually begin to see all of that hydrogel popping out. That is quite something. Let's see. Oh. This is actually really dry. It's a little bit damp on the surface of it. And certainly I wouldn't recommend eating it or licking it or anything, but that is, there it all is, expanded. There's actually several layers of it in here as well. But that is all the water we poured in earlier, all inside those polymers, expanded into gel. Because there's still mostly water in there, it's just held in place well by hydrogen bonding. Not just the water with the polymer, but the water bonding with itself. So this wouldn't absorb oil or ethanol or other molecules anywhere near as well as pure water. And the salts and other compounds in urine do reduce the efficiency a little bit, but this tiny amount of polymer, barely a gram actually in the whole nappy, is still more than enough to keep an infant dry overnight. There are many types of these polymers and hydrogels with lots of different uses, including some food additives that help hold on to moisture, or even bulk them out without adding calories. But does the chemical really have to be a polymer? It turns out, yes, it does, because we can look at carboxylate groups when they're not attached to polymers. For example, sodium acetate. Might not be familiar with it, but you'll recognize it as salt and vinegar flavoring. It's not like a nasty chemical additive thing. It's literally what you get when you mix salt and vinegar together. That also has a really interesting relationship with water because its solubility is absurdly high. You can keep spooning this stuff into water and it will just nicely dissolve in it. You can dissolve over 1,000 grams of sodium acetate per litre of water. So by mass at least, that's more sodium acetate than water. But it still remains liquid. It doesn't absorb water and remain as a controlled solid gel-like substance as the polymer does. So it's not just the molecular level chemistry at work here with functional groups holding on to water. It's a whole lot of material science and polymer science going on. There's the cross-linking and the kind of the almost macroscopic structure of the polymer too, all going towards making this a really efficient hydrogel and a bit of chemistry that makes life a little bit easier.